everybody, and welcome back to another spicy episode of Maths. Hope you're all having a great day so far. In the last couple videos, we were kind of getting a little experimental and looking at what order of operations could have been. We saw that, okay, what would happen if we defined order of operations differently? Could we still get some interesting stuff and some consistent stuff? And also what would happen if maybe we just didn't have order of operations? We saw that we could actually still evaluate expressions consistently by using a little workaround with parentheses. But that was largely just kind of a what if questions, food for thought, nothing that we're going to be using a lot of in actual math moving forward, because at the end of the day, we've already got a set order of operations that everyone uses. So kind of returning back to order of operations now, what I want to do today is go through another kind of visualization of the order of operations that we use, and some people may find this kind of a useful perspective on order of operations. And yeah, so these are called expression trees.
Expression trees.
Let me take a statement like 3 plus 4. The way we're going to write this in an expression tree is we're going to kind of have these nodes that are connected with these edges. So we'll take the 3 and the 4, and what are we doing? Well, we're combining the 3 and the 4 through addition. So this expression 3 plus 4 would be written like this inside of the expression tree. Similarly for subtraction, multiplication, and division, it's all going to look very much the same. And we could also throw exponentiation in there if we wanted. And in case you haven't seen the exercise video for what if we define order of operations differently, this was kind of one symbol that we used to denote the exponent, where we're doing 3 to the power of 4. So 3 to the power of 4, that's the same thing as that. This is just a common way of writing it when we don't really have an easy way of putting it in the power. So oftentimes when you're typing things out, this is the way to write 3 to the power of 4 on your computer. But in any case, we have a nice way to express all of these things. Now you might be thinking, well, Maths, you're missing parentheses. Well, I'm actually not, and that's kind of a nice thing about these expression trees, is we don't need parentheses when we use them. Let me show you how. So let's say I have something like 3 plus 4 times 2. With regular order of operations, the way we would do this is we take 3 and 4 and 2. And order of operations, we know we do the 4 times 2 first. So what we're going to do is we're going to combine the 4 and the 2 with the multiplication here. And then afterwards, we take that result and we add it to the 3. So then we take an addition node here and we write something like this. So how this is interpreted is we do 4 times 2. That's going to give us a result here, which in this case will be 8. And then we take that result and we add it to the 3. Right? So it's a nice way of writing it. Now, where parentheses stop being necessary is because in order of operations, if I wanted to prioritize the addition first, doing 3 plus 4, all of that times 2, well, it's really easy in this method, right? All we have to do is just take the 3 and the 4, and then add them together with an addition node, and then take that result and multiply it with a 2 with a multiplication node. So notice what we end up getting. We are able to prioritize the 3 and the 4's addition by simply just having it come first before we do a multiplication node. And so in this way, we're not really using parentheses because the order is purely based on the structure of the expression tree. All right, so let's try maybe a little bit more of a complicated statement. All right, so what would this look like inside of an expression tree? So what we can start with is we can just start by writing all of the numbers that appear here, and then we're going to figure out how to combine them. So we'll have 7, 8, 3, don't forget the exponent, 2, 7, and 1. Okay, and then following order of operations, the first thing we're going to do is 7 plus 1. So we'll do an addition node to combine them. And then following order of operations, next up we have exponentiation, right? BEDMAS, E comes next. So we'll do 8 to the power of 3 next. So that's 8 to the power of 3 with an exponentiation node. All right, now we have multiplication and division. Doesn't matter the order we do them. 7 times 8 cubed, so we're going to be combining this 7 with the result of this exponentiation subtree, we could call it. And that represents this piece here. And now we can do 2 divided by this part right here. So I'm going to put a division node right here. And we're going to be doing 2 divided by the result of this subtree right there. And then we're just taking these two parts and we're subtracting them. So we take the result of this tree here, and we do that minus the result from this tree right here. So this would be the expression tree for this statement right here. So now let's start with an expression tree and see how we can maybe evaluate some things with it.
Evaluating and converting from expression trees.
Okay, so if we're going to evaluate this tree, we can start by looking at the kind of smallest tree. So that's the 6 minus 12. If we didn't think about that and we said, okay, what's 2 times? But then the problem is we're multiplying it with this part here, but we don't know the result of that yet. So just kind of working down, the first thing, the only thing that we can focus on is this part right here. So 6 minus 12, that becomes negative 6. So we can just kind of keep track of what number we get along the way. So now we're doing 4 plus negative 6, which is the same thing as 4 minus 6, and we're going to get negative 2. And now we're doing 2 times that result, so 2 times negative 2 is negative 4. All right, so then our whole result for this expression tree is negative 4. Now, if we wanted to write this expression tree in terms of just a regular expression where we're not using a tree, so we just kind of follow the tree. So what did we do first? We did 6 minus 12, right? So 6 minus 12, and so let's put that in parentheses. And then next up, we did 4 plus all of that. So we do 4 plus this statement here. And then lastly, we did 2 times that entire thing. So we're going to put this all in brackets once again, and we're going to do 2 times that. Now, we can remove this pair of parentheses right here. It's not necessary because if we do 4 plus 6 minus 12, that's the same thing as if we did 6 minus 12 first and then added the 4 on after. So we get 2 times 4 plus 6 minus 12 would be a simplified version of this expression. But either way, we evaluate that to negative 4. All right, let's try another one. All right, so for this statement here, where it's a little bit bigger, but we're just going to kind of work through what we can evaluate. So we can actually evaluate any of these three. We can do 8 divided by 2, so that is 4. 3 plus 2 is 5. 7 to the power of 2, 7 squared, that's 7 times 7, which is 49. All right, perfect. So kind of everything on this layer is done. Now we can focus on this multiplication and this addition. So 4 times 5, that is 20. And 49 plus 1, that is 50. Now we're looking at 20 divided by 50. 20 divided by 50, that is 2/5 or 0.4. So we could do either of these for the answer. So once again, not bad, right? All we're doing is we're just evaluating this expression tree by kind of following the path. And it's quite nice because we can only do things that are possible, right? We couldn't do the multiplication before we did this division or this addition here. And so we're basically forced to follow an order, right? Because if we tried to do this multiplication first, we wouldn't be able to because we don't have the numbers 4 or 5 yet, right? And to write this out as an expression, let's see what we have. So we have 8 divided by 2, and we have 3 plus 2, and these were being combined through multiplication. And then over here, we had 7 to the power of 2, plus 1. And then this result right here, and this result right here, we divided them. All right, and we can remove some unnecessary parentheses. Since we move from left to right, we don't need the parentheses right here. So 8, we could do 8 divided by 2 times. And then we need the 3 plus 2 because order of operations doesn't prioritize the addition. And then divided by, and then 7 squared plus 1. We do need the parentheses because we want this addition to come before this division. And since we're moving from left to right, we technically don't need these parentheses either. But as we talked about in the order of operations video, it might start looking kind of ambiguous with the division, multiplication, division. So let's just leave it like this. But either way, we know this expression evaluates to 2/5 or 0.4. Now, one really nice thing about these order of operation trees, in addition to being maybe a little more clear as to what we can evaluate first, we also actually get a kind of nice little additional detail where we kind of talked about in the past that we can evaluate kind of some things at the same time. So, for example, when I had an expression like 3 times 4 divided by 7 minus 3, even though multiplication comes before subtraction, we're able to really evaluate this 3 times 4 and the 7 minus 3 at the same time because they're not interacting with each other, and they're going to be evaluated before we do this division, which will make them interact with each other after. So we can evaluate these kind of at the same time. And I think this expression tree makes that a little more clear where, yeah, we can evaluate this 8 divided by 2, this 3 plus 2, and this 7 squared all at the same time. Even though division, addition, and exponentiation occupy different places in BEDMAS, because of the way they're separated in the expression, it doesn't actually matter which one we evaluate first. And we see that quite clearly inside of this tree. Because they're all separate from each other, right? They don't get combined until later on. We can actually evaluate them all by themselves, and it doesn't matter. It didn't matter if I did the 3 plus 2 first, or the 7 squared first, or the 8 divided by 2 first, right? Because they're not getting combined until later on. So I think that also makes that point more clear.
Concluding thoughts.
Okay, so that's going to do it for me today. I hope you found this video interesting. It's just another perspective that we have on order of operations. Obviously, it's going to be more convenient in the long run, more efficient in the long run to just evaluate expressions like this, but it is a nice visualization of what's going on, and it might make some of the kind of concepts and some of the points of order of operations make a little more sense to you. So I encourage you to do some practice. I'm going to come out with a video, of course, for some exercises, but just try and practice converting between these expression trees and the expressions themselves. But until the next episode, you have a good one, you stay groovy, and I'll see you then.
F.O.A. Maths.